In a previous video, we saw how a spring with mass m and its free end moving with speed v had a kinetic energy of 1/6 mv squared. Now we'll see how the mass of a spring relates to its angular frequency. To do that, we'll consider the equation for the total energy of the spring. The total energy of the spring is composed of its kinetic energy and its potential energy. E is the total energy of the spring. As we see above, the kinetic energy of the spring is 1/6 mv squared, and the potential energy of the spring is half kx squared, where k is the spring constant and x is the displacement from equilibrium. V is the derivative of x over time, so let's write that. For a spring oscillating in simple harmonic motion, its displacement x equals a cosine omega t, where a is the amplitude of the oscillation and omega is the angular frequency. The derivative of x with respect to time equals minus a omega sine omega t. Let's write these values into our formula. m/6 negative a omega sine omega t plus half k a cosine omega t squared equals to E. We see a sine squared plus a cosine squared, and the value on the other side of the equal sign is a constant. This reminds me of the trigonometric identity sine squared omega t plus cosine squared omega t equals 1. So let's try to get this equation here to look like this equation. We'll square the values in the brackets and then divide both sides of the equation by E. M a squared omega squared, and the negative sign becomes positive after it's squared, divided by 6 times sine omega t, and that's squared, plus k over 2 a squared cosine omega t squared equals to E, and let's divide both sides by E. So this equals to 1. We get E here, and we get E here. We see that the coefficients for sine and cosine are 1. This means that this part equals to 1 and this part equals to 1, and they both equal each other. So let's write that. M a squared omega squared divided by 6e equals ka squared over 2e. When we multiply this side by 2e, this equals to 1. And when we multiply this side by 2e, this equals to 3. The a squares cancel out. So omega equals k over m divided by 3. And there's a square root. So we see that the angular frequency for a spring with mass m is the square root of k over the mass divided by 3. Let's see what happens when we have a spring with mass m, and its n is moving at speed v, and there's a block at the end of it. And this block is m sub b. What is the total energy of this system? So we have the kinetic energy plus the potential energy. That equals the total energy of the system. So the kinetic energy from the spring is 1/6 mv squared, and the kinetic energy of the block is half mb v squared, and the potential energy is the same, half kx squared equals to E. So let's try to group the variable v squared. One over 6 m plus 1/2 mb plus 1/2 kx squared equals E. We'll replace v with dx over dt, and we'll use the values that we found over here. mb over 2 negative a omega sine omega t squared plus k over 2 a cosine omega t squared, and this equals to E. Now let's try to make this equation here look like the equation in yellow. M over 6 plus m sub b over 2 times a squared omega squared sine squared omega t plus k a squared over 2 cosine squared omega t, this equals to E. And when we divide both sides by E, this becomes 2E, and we'll divide this by E. So this part right here and this part right here equal to 1, and they equal to each other. So let's write that. M over 6 plus m sub b over 2 a squared omega squared over E equals ka squared over 2E. The a squares cancel out. The E cancels the E. And when we multiply both sides by 2, this equals to 1, this equals to 1, and this equals to 3. So we have the angular frequency equals k divided by the mass of the spring divided by 3 plus the mass of the block, and we have a square root. For a system where the spring has negligible mass and the block has mass m sub b, and this system is oscillating in simple harmonic motion, its angular frequency is k over mb. We see that if we want to consider a spring's mass in the equation for its angular frequency, we need to add its effective mass, m over 3, to the mass of the block.